In electronics, a diode serves a single, uncompromising purpose. It allows electrical current to flow freely in one direction, but if that current tries to reverse course, it hits a dead stop. Physically, this component usually looks like a small black cylinder with a silver stripe painted on one end. That painted stripe corresponds directly to the flat line on its engineering symbol, identifying the cathode end, with the opposite side being the anode. Traditional electrical engineering drawings use what is known as conventional flow, which visualizes electricity moving from the positive terminal to the negative terminal. But the physical reality of a circuit is electron flow, where electrons actually travel from the negative terminal toward the positive. We are going to track true electron flow to see exactly what is happening inside this component. The engineering challenge here is immense. We are achieving absolute directional control over a torrential flow of electrons, and we are doing it without using a single moving mechanical part. To understand how this silent, motionless valve works, we must look past the macroscopic circuit and engineer a solid-state crystal from the atomic level up. At its most basic physical level, electricity is simply the movement of free electrons passing from one atom to another. In a conductive metal like copper, the outermost ring, the valence shell, physically overlaps the conduction band. Because of this overlap, electrons are barely held by the nucleus. They slip right into the conduction band and drift freely. An insulator, like rubber, is the exact opposite. Its valence shell is tightly packed with a massive gap to the conduction band, trapping electrons entirely. Current cannot flow. Standard materials are entirely locked into their natural states. They either pass electrons freely or they block them entirely. To build a directional valve, we need a specialized third option that we can manipulate. This is where semiconductors come in. Materials like silicon sit perfectly between an insulator and a conductor on the periodic table. A single silicon atom has 4 valence electrons. When clustered together, these atoms lock into a rigid lattice, perfectly sharing their electrons with their neighbors in tight covalent bonds. Because every single electron is accounted for and locked into a bond, pure silicon actually acts as a very stubborn insulator. Through doping, we inject alien atoms to destabilize the lattice. In N-type doping, phosphorus adds 5 electrons, 4 form bonds, leaving the 5th unbonded and free. In P-type doping, aluminum brings only 3 electrons, leaving an empty void, a hole where a 4th should sit. We have now weaponized pure silicon into 2 highly unstable materials. The N-type is packed with excess free electrons, and the P-type is riddled with empty holes desperately seeking electrons to fill them. The real physics begin when we physically press these 2 engineered materials together. The moment they touch, excess electrons from the N-type side rush across the border to occupy empty holes on the P-type side. This migration creates a localized buildup of negative charge on the P side, leaving a positive charge on the N side. This localized electrical wall is called the depletion region. Because negative charges repel other negative charges, the buildup along this border eventually becomes strong enough to push back against the remaining free electrons, permanently halting any further migration. In a standard silicon diode, the physical wall created at this junction exerts a potential difference of roughly 0.7 volts. The only way electricity flows through this component is if an external force greater than 0.7 volts is applied to punch through that barrier. This self-regulating electric field is the literal mechanism of the diode. We have engineered an invisible gatekeeper directly into the solid crystal. Now we wire this PN junction to an active power supply to see the valve in action. In forward bias, we connect the battery's negative terminal to the N-type side and positive to the P-type. Exceeding the 0.7 volt threshold physically collapses the depletion region, allowing a torrential flow of current to pour entirely through the crystal. Flipping the battery creates a reverse bias. The positive terminal pulls internal electrons to the N-type's edge, while the negative pulls P-type holes the opposite way. This stretches the depletion region, turning the crystal into a perfect insulator, stopping all flow. By merely changing the direction of external electrical pressure, the internal architecture immediately reconfigures itself. We have our switch, with 0 moving parts. Engineers do not visualize atomic lattices daily to build circuits. They rely on data visualizations to predict how a component will react under pressure. This IV graph plots a diode's characteristics. Forward voltage remains flat until breaching the 0.7-volt barrier, where it spikes upward into massive current. In reverse bias, it holds zero current until hitting the breakdown limit, destroying the crystal. This single curve mathematically validates the physics we just built, and it serves as the ultimate reference for sizing diodes safely in modern electronics. The most critical application of this solid-state valve is controlling the volatile nature of alternating current. AC power moves electrons forwards and backwards in an oscillating sine wave. A single diode provides half-wave rectification. It allows forward positive surges to pass, but instantly chops off the wave when it pulls backward. While this does stop the alternating flow, it is incredibly inefficient. We are completely blocking and therefore wasting half of the generated power. The engineering solution is full-wave rectification, which utilizes a precise geometric arrangement of 4 diodes known as a bridge rectifier. Instead of blocking the reverse flow, this bridge routes those backward-moving electrons through an alternate path, effectively forcing them out in a forward direction. By adding a capacitor to the end of this circuit, those pulsating forward humps are smoothed down into a clean, flat line of direct current. By strategically arranging these atomic barriers, engineers tame the volatile oscillation of AC power into the highly stable DC supply required to run modern electronics. We can verify all of this highly theoretical physics right down on the technician's workbench. When you probe a diode using the test function on a multimeter, you are physically measuring the strength of the atomic depletion barrier we built. A healthy silicon component will require roughly 0.7 volts to open in the forward direction. When you reverse the test leads, the meter will read OL, or out of limits. That out of limits error confirms the internal crystal structure is perfectly intact, blocking the current and proving the solid-state valve functions exactly as engineered.